Hello, class. Okay, so last time we were talking about Gauss's law, and now we're going to talk about conductors and kind of how Gauss's law can apply to this as well. So we're going to start out. Let's say we have a metal. Could have, say, like a rectangular object that is, say this is like iron or aluminum or copper. It's a good electrical conductor, and it's electrically neutral. So if you look at any region, the same number of positive and negative charges. And basically the way a conductor works, what makes this a conductor is, let's take copper. This is made out of copper, where each atom has 29 protons. So if you have a copper atom, like a typical copper atom by itself has 29 protons, 29 electrons. When you put them together in bulk and have a large object made out of copper, this is basically true as well, that every atom has 29 protons and 29 electrons. However, one of these electrons is very weakly bound to the atom. And so if you apply an electrical field, we know electrical fields exert forces on charge. So there will be a force on that electron that can easily pull it away from the atom. So in a sense, you have, like, every atom gives up one electron that's kind of free to move around the metal. It's typically bound to the metal, though. Like if you try to remove it, let's say you take an electron and remove it. So you take an electron outside of the metal. Well, the metal is electrically neutral, and so that's going to leave a positive charge on the metal, which is going to attract this electron. So they can move around fairly easily inside, but that's it. You can remove them, but that takes a lot more force than we're going to be dealing with. So the electrons are free to move around, but they're not going to leave the metal overall. Okay, so that's basically what a conductor is. And again, it has one free electron per atom. We've already talked about, like atoms, moles in Avogadro's number. So if you have like even a small metal wire or something, the amount of electrons that are free to move around is, effectively infinite for the kind of problems we're going to be dealing with. So we can actually say just, we can move around as many electrons as we need. Now what happens if we apply an electric field? So let's say we have an external electric field. So I'll say an external electric field. Now, this electric field is going to exert forces on all these electrons, and so we're going to have electrons that are moving to the left. So remember, the force on a negative charge is in the opposite direction of the electric field. So we're going to have electrons that are going to move to the left, but they have to stop when they get to this end here. So we'll have a buildup of electrons on the left end. We can't remove them entirely from the material. And this conductor is neutral overall. And so we're going to have positive charges building up on this end. So again, electrons from like the whole thing are going to just shift to the left. And so we'll get this charge separation. And this will create an internal electric field. Like, forget this external field for a moment. If you have positive charges here and negative charges here, you'd have an electric field from the positive to the negative. So we have this, I'll call this an internal electric field due to the charge separation. And so they're pointing in opposite directions. So overall, the electric field inside the conductor, let's just look at the magnitude of the electric field inside the conductor. That would be magnitude of the external field minus the magnitude of the internal field. And I'm just going to state this is going to be 0. Yeah, I'll talk more about that in a minute, because it's not always true. But basically, if you just set up an external field, this is what's going to happen. So why is the electric field going to be 0 inside? Well, what if the electric field inside is not 0? Then the charges, or there's going to be forces on the charges, which will cause them to move. So initially, like say you just turn on this external field, you'll get some charges, if you just look at a short time later, these charges have to actually move around, and that takes some time, not too much for a good conductor, but, it's, initially you're going to get these small charges building up on the edges, which result in a small internal electric field, so there's still going to be a net field pointing to the right. But the longer that condition exists, it's going to continue to cause the charges to separate and build up this internal field. And so the charges will continue building up on the edges until the electric field is 0. And so, if it's not 0, then charges are still moving around. So if you just create an external field and leave it, this is going to be the end result, that the electric field inside the conductor is 0. Now, it's essential that we kind of set up this external field and just leave it alone. So if we had this condition, say we turned on an external field, waited until the charges were separated enough to build up a sufficient internal field so that the overall field in the conductor was 0. If we suddenly changed that external field, like say we made it stronger, that would mean the electric field inside the conductor was no longer 0, but then charges would continue to separate and build up on the edges, and so the internal field would respond and eventually set this back to 0. So anytime you have like a static electric field, this is what's going to happen. But don't think the electric field inside a conductor is always 0, because I can give you an example where the electric field in a conductor is not 0. Let's say we have a copper wire, and we do this to it. We make a loop, and we hook it up to a battery. So we have to make a loop so we don't have a nice, straight line anymore. But in a case like this, we are going to have an electric field that loops around following this wire, and that electric field is not going to be 0 because of the battery. So, inside the battery you have ions that move around and separate these charges, and so that's going to maintain that external, or maintain the electric field inside the wire. And because there's this, this maintained electric field inside the wire, these charges are going to continue to move, and that is what we call an electrical current, which we're going to talk about later. And so again, if you just hook up wires to a battery, you'll get an electrical current, which is very useful. And so again, this is not a static system, though. There's actually things happening inside the battery that maintains that electric field and just keeps these chargings from building up sufficiently to cancel the external field. So don't think the electric field inside a conductor is always 0. Obviously, this is an important case. If the electric field inside a conductor is always 0, things like batteries wouldn't, or electrical circuits would not really exist. So we're talking about a purely static case here. Okay, so let's kind of look at Gauss's law again. I'll just write that down. Where we've got electric flux. We use a Greek letter phi for electric flux. And again, like E is the electric field, A is the area of a surface. And we have a normal vector. So if we have a flat surface, it has a normal vector. And this electric field can make an angle with respect to that normal vector. That's that theta there. So that would be the electric flux, which is a measure of how many electric field lines are crossing through that surface. Okay, and then what Gauss's law says is that the flux through any closed surface is equal to the total charge enclosed over epsilon naught, where this is that constant. So it's related to Coulomb's constant, like 9 times 10 to the 9th. That's equal to 1 over 4 pi epsilon naught. But we kind of have two fundamental ways of looking at electric forces. One is Coulomb's law, one is Gauss's law. So we have two constants, just whichever is convenient for whichever approach you're taking. So let's look at how we can apply Gauss's law to a conductor. So earlier we found that Gauss's law in some rare cases can be used to actually calculate electric fields. That's very unusual. There's only a few cases where the geometry works out just right. So what we're going to do is, let's say we have a conductor, and say it's neutral. So this is a neutral conductor, and let's say there's a cavity inside it. So you can picture like a spherical shell, which has something hollow inside, where it could be any shape. And overall, it's neutral. And let's say we place a charge inside the cavity. So let's place a charge here. We'll just place a single charge, Q1. And so what's going to happen, like before this was, the conductor's electrically neutral, and it's going to remain electrically neutral, unless Q1 was extremely strong, where it could actually rip electrons off of the metal, but let's say that's not going to happen. But this charge is going to create an electric field in the region of this conductor, and we know the electric field inside the conductor is going to be 0, because this is a static case. We just place the charge there and leave it. So it'll take some time for the charges to move around and adjust themselves, but once they do, we'll have that static case where the electric field inside is 0. And so charges are going to move around. And exactly how they're going to distribute themselves to wipe out the electric field inside, that's actually fairly complicated. But we know that, we're going to see anyways, that the charge can only exist on these two surfaces. So let's call this surface 1. The outer surface, let's say that's surface 2. So we can have charges building up on those surfaces, but let's say we have a point A. And what I'm going to say is that we cannot have a net charge at point A. And the reason why, let's look at this point, and let's draw a Gaussian surface around it. So point A is completely enclosed by this Gaussian surface. And what can we say about the flux? Let's just call this surface A, Gaussian surface A. If it's enclosing point A, the flux through that surface has to be 0. The reason why is the electric field is 0. Because this entire surface is contained inside that conductor. And so the electric field is 0 everywhere, and so the flux is 0. And that means the total charge enclosed by that surface is 0. So the total charge at point A, here, let's do it like this. The total charge at point A is 0. Because we can make this Gaussian surface as small as we want. So we could just completely contain it right outside the charge. And so that's a net charge. So we can have protons and electrons at that area, but they have to occur at equal numbers. Equal number of protons and an equal number of electrons. But that's not going to be true at point B. Let's say we look at point B on the surface. And remember, for Gauss's law, we have to draw our Gaussian surface has to completely enclose the charge. And so if we draw a Gaussian surface around point B, no matter how small it is, we can say the electric field of this part is 0. But the electric field outside does not have to be 0, so we can have a flux through this surface here. So we cannot say Gauss's law implies that the surface, or the charge at some point on the surface, that does not have to be 0. Because, no matter, we have to enclose the surface, and so there's definitely going to be some of the surface outside of the conductor where we can have an electric field, so there can be a flux through this surface. So the charge on the surface, we can do the same for the inner surface as well, where some of the Gaussian surface would exist inside the cavity, where the electric field does not have to be 0. So the charges at any interior point, the net charge has to be 0, but we can have charges on the surface. We basically have to have charges on the surface. Because, this creates an electric field, so charges have to move around. And, they can't build up anywhere inside, so the only place they can really go where we have a net charge is on these two surfaces. So the question is, how much charge is going to build up on each surface? And we can actually answer that with Gauss's law. Let's draw a Gaussian surface around this cavity here. Now let's make this a little more concrete. Instead of saying Q1, I'm going to say we have a charge of, say, 1 coulomb. So that's a charge of positive 1 coulomb. So you might guess, what type of charge is going to build up on surface 1? Obviously, it's going to be negative charges. We place a positive charge in this cavity. The negative charges are going to want to go, as close as they can get to this charge. So they're going to build up on the surface. So we should expect a negative charge on surface 1. And then we should also expect positive charges on surface 2. Because these are like the leftover charge. And so the question is, what's the total amount of charge that's going to build up on surface 1? And again, we draw this Gaussian surface here. Let's call this surface 1. And we know that the flux through surface 1, again, has to be 0. Because our Gaussian surface is completely inside this conducting metal, and where the electric field is 0, and so the flux is 0. And so the total charge enclosed in this Gaussian surface is 0. So we can say Q enclosed, and I'll just call it Q1, has to equal 0. And so what we have is Q1, the total charge in this Gaussian surface. That would be that 1 coulomb charge we placed in the cavity, plus the charge on surface 1. And so the total charge that builds up on surface 1 would have to be minus 1 coulomb. So we're getting a negative charge as expected. And so, the charge on surface 1 would be negative 1 coulomb. So we put positive 1 coulomb inside the cavity, and we have negative 1 coulomb in total distributing around that surface. Now, how it actually distributes, it's fairly complicated, and we're not really going to get into that. I will just say this, it depends on what the surface of the cavity actually looks like. And it turns out when you have, like, say we have a surface like this, turns out you get most of the charges building up like around this sharp point, and in regions with very little curvature, like in these flat regions, you'd have very little charge, but it builds up more around these curves, and definitely if you have like a sharp point, you get more charges building up there. But actually figuring out like what it would look like, we're not going to get into that other than just saying it, builds up on sharp points, not so much on flat surfaces. But we can say that however it distributes itself, if we have 1 coulomb inside, there's minus 1 coulomb spread out over the entire surface 1. Now what about the charge on surface 2? Now we can't use Gauss's law here. Yeah, there's no way we could really draw a Gaussian surface that's just going to answer that question for us, because we don't know what the electric field looks like outside. And if we draw a Gaussian surface inside, that won't include these, the Gaussian, from Gauss's law, it only applies to the charges inside. So it won't tell us anything about, if we draw something inside the cavity, it won't tell us what's going on with the charges outside. And if we draw a Gaussian surface outside entirely, then we don't know what the electric field is, so we can't actually calculate the flux. However, it's actually very easy to answer this question. What is the charge on surface 2? And that's plus 1 coulomb. Why is that? Well, we know that -1, we know to start out with, this conductor is electrically neutral. And so if we place this charge inside the cavity, we know a total of 1 coulomb of negative charge is going to build up on this inner surface. So where did that negative charge come from? It came from the conductor itself. And so there has to be 1 coulomb, like a positive 1 coulomb, somewhere. Other than this inner surface, we have to have positive 1 coulomb somewhere, but it can't be anywhere in the interior of the conductor, because we know, like at any point we look at, inside the conductor the charge is 0. So the only place that, that this charge can exist is on the outer surface. So we have this separation of charges, like 1 coulomb of negative charge builds up on surface 1, and 1 coulomb of positive charge builds up on surface 2. So again, if you add up those, you get 0. So charge is just moved around, but we still have the same amount of charge. So again, this is another application of Gauss's law. Sometimes we can use it for calculating electric fields, and then we can also look at answer some questions that would otherwise be fairly complicated, but they can be made kind of simple with Gauss's law. And just one more thing I'm going to say about this. Students often get this wrong, because I think a lot of students get it right as well, but when I'm grading it, like, we're going to erase this and just, okay, let's say we have, I'll just redraw it. Let's say we have, like, say, 2 coulombs, so we'll make a separate problem. 2 coulombs here, and if I ask, like, what's the total charge on surface 1? What's the total charge on surface 2? What I kind of frequently get would be like the charge on surface 1 equals 2 coulombs, and the charge on surface 2 is minus 2 coulombs. I'm going to put a line through it just in case you look without, like, listening for whatever reason. But yeah, it's a very common response. So again, what I would recommend, well, apply Gauss's law correctly. That's the first thing. But also just think, we have positive charges here. So what should happen is, even without thinking about Gauss's law, If you place a positive charge, that's going to attract negative charges. And so these negative charges are going to get as close to that positive charge as they can. And so we should expect a negative charge on surface 1. So if you, just kind of think in terms of basic attraction of charges, the charge on surface 1 has to be negative, and that would leave a positive charge on surface 2. So again, a common mistake. And so just watch out for that. And actually that's it. I label this lecture Conductors, but we're talking about one very specific thing. Maybe I should have called this Conductors in Gauss's Law. But we'll leave it at this.